A radioactive isotope of carbon has more nucleons than non-radioactive isotope. So probably they're talking about carbon-14. We see carbon-14 as an example when the first time we talk about isotopes. With chlorine, right? Chlorine 35 and 37, carbon 12, carbon 14. How many protons, neutrons, and electrons could there be in this radioactive isotope of carbon? Now, one thing to note about elements are, if something has a different number of protons, it's a different element. Quite literally, the number of protons is what determines an element, right? You take carbon, you throw one more proton into it, it's not carbon anymore, it's nitrogen. At least I think it is. I think that has 7 protons, right? So this over here is not cool. This is not right. So C and D and R are out. So what's left? This is just carbon 12, the one over here, right? So over here, this is identical to A. So this is not an isotope of A. The only correct answer, which is an isotope, is B. All right, that's our answer, guys. Interesting question. Graphite is often used as the electrode in electrolysis of solutions. I'm not sure why this is confusing people. Graphite is straightforward, right? So its conduction behavior, even though it's not a metal, is very similar to metals because of that one delocalized electron by carbon, right? Which particles are involved in the conduction of electricity by graphite? I guess there's a strong chance of misreading the question, and I guess people thought they were talking about the solution rather than graphite. It's electrons only, and that's it. Negative ions, no. Like it's just it's just the electrons. Everything else is wrong. Negative ions don't really, aside from a solution, but that would also be positive ions. And this is just, I mean, I don't even know. It's more or less rubbish. And it's electrons only. That's our answer. Iodide ions are readily blank, right? So let's take a look at iodide ion. There's only one kind of iodide ion which has a negative charge. So what it can do is, two of these can lose electrons to form iodine. What is the loss of electrons called? It's oxidation. This has been oxidized. Isn't that true? Positive result for the test in which the solution changes color from blank to blank. Okay, so iodine is formed from iodine ions. At this point, this is colorless. The ions are colorless, and this would have a brownish color, right? So what's the correct answer? Oxidized? Oxidized, colorless to brown. B is our answer. Oops. B takes so long. B is our answer. All right. Bitumen, diesel, naphtha, and paraffin, kerosene, are all fractions obtained by fractional distillation of petroleum, which gives the correct answer. Bitumen is a source of polish. Well, they put it's roads, right? They use it to make roads. Diesel, it's a fuel for heavier engines, but not aircraft engines, right? But it is a fuel, and I think most people got this wrong because of this. Actually, this is one of my least favorite questions because it's just recollection. It's a rutta, as we say it. Naphtha, a fuel for heating. Normally people, get confused with naphtha. Naphtha is the term used for feedstock for the plastic industry. Anything that goes to the plastic industry is feedstock for that industry. Paraffin is, or kerosene is, used as cooking oil. So our answer over here is D. But this is more of a recollection question. Like there's one table in every book talking about these things. We just have to, familiarize ourselves with them. Aqueous copper sulfate is electrolyzed using copper electrodes. The current is constant and the anode positive electrode is weighed at regular intervals. Which graph is obtained when the mass of the anode is plotted against time? Right? Now copper electrodes, what's happening to the positive electrode? And the positive electrode is going to be made out of copper, and it will be discharged because it's going to take away its electrons and produce, right? And it's going to produce copper ions. Now from a solid, it'll turn into a solution because the ions will dissolve in the solution, right? So what's going to happen to the mass? Well, more and more copper is leaving, the solid copper is leaving and turning into ions, right? Now B and D are out. B is out and D is out because they're talking about the mass of the anode increasing. Now, is it decreasing at this way, or like is it constantly decreasing? How do we find that out? Now, the current is being supplied constantly. Current is supplied, or electrons are supplied to the negative electrode. But can I also say the electrons are, because the current is always the same in any point in the circuit from physics knowledge, the electrons being taken away are also at a constant rate. And if they're going away at a constant rate, copper turning into copper ions is also constant, right? So which is it? Which one is it? So is C the answer? It's talking about it constantly? Yes, it is. C is our answer. Which substance is not a raw material used in the manufacturing of sulfuric acid? Well, you take the oxygen from the air. Sulfur you get from your fossil fuels, right? Sulfur dioxide. You use the sulfur. I'm glad sulfur is here because it helps me explain it. You take the sulfur and turn it into sulfur dioxide. So technically, it's not a raw material. You need sulfur dioxide in the process. Eventually, if you had it, you wouldn't need sulfur, but you can find sulfur dioxide naturally in large quantities. So your raw material, the main ingredient in sulfur, which turns to sulfur dioxide, then sulfur trioxide, then oleum, then sulfuric acid. The structural formula of some organic compounds are shown below. Which compounds are alcohols? So let's identify the alcohol function group. That's alcohol, isn't it? Hash another alcohol. That's a diol, as they say, but we don't need to know if it's a diol or not, but technically it's an alcohol. Is this an alcohol? Last one? No, it's not, because that actually is a carboxylic acid function group. But sir, it has an OH here on the carbon, so doesn't that make it an alcohol? No. Having the double bonded O connected to the carbon at the same carbon where the OH is bonded to it will give it different properties. It behaves like an acid, right? So an alcohol is ONH to the carbon with nothing else on it aside from carbons, or it could have other carbons, right? Kind of like this. But it's just a pure OH thing, right? So 1, 2, and 3 are alcohols. Just for fun, let's try naming them. Number 1 is propanol. Propanol. Number 2 is, and this is more for IGCSE kids, it's propan-2-ol, not for O-level kids, propan-2-ol, and that's just difficult to name, so I won't. It's actually propan-diol, propan-1,3-diol, or something like that. but we don't need it. That turns into an A-level challenge. The last one is propanoic acid. Propanoic acid. Right? Let's move on. Which process is suitable for obtaining water from an aqueous solution of sugar? Now note, they want to extract the water from the sugar. I think distillation is the way to go, right? Because distillation is evaporation where you collect the whatever's being evaporated. So that's it. That is it. Why can't you use crystallization? Crystallization is more of a, you lose the water but you obtain the sugar, right? Because you'll get sugar crystals. Filtration, sugar is soluble and will not separate. And separating funnel, what good will that do? But okay, distillation is it. Alright, some ion talk. So an ion or any atom will have protons, it'll have electrons, and it'll have neutrons, right? And they're talking about X positive, the sum of protons, and I should have gone the other way, electrons separately, P, N, and E, right? And it has the sum of protons and neutrons is 23. This entire thing is 23, right? And it has 10 electrons, right? So if I move down and if I have just X, well, I'm not changing its nucleon number at all, so it'll still remain 23. That looks like 23 to you guys, but it's gaining 1 electron because it doesn't have that positive charge anymore. And this is the atom, right? So I know how many protons it has because it should match the number of electrons on a nuclear charge or neutral charge. So it has 11 protons. It had 23 nucleons, 11 of which are protons. So 23 minus 11 is 12. It should have 12 neutrons. All right? So what's matching what? 11 protons and 12 neutrons. The diagram shows the molecule ethyl propanoate, right? Consider all the electrons in the molecules of ethyl, all the electrons in ethyl propanoate. How many electrons not involved in the bonding are there in the molecule? So how many electrons are not involved in bonding? Okay, right? So here's a different way of doing it. Let's see if we can work it out. Completely guessing, like completely just thinking of this. Let's find an efficient way of doing this. So carbon, there's carbon present, there's hydrogen present, and there is oxygen present over here. And carbon has 6 electrons, hydrogen has 1 electron, and oxygen has 8 electrons, right? But each of how many of these do we have? Like 1 carbon, 2 carbon, 3 carbon, 4, 5. Ethyl propanoate, right? That has to be 5. So 6 times 5. And how many hydrogens? I count 3, 4, 5, 6, 7, 8, 9, 10. 10. How many oxygens? I see 2 oxygens. Right? What is this? What is this coming out to? Okay, 6 times 5 is going to be 30. 10. 8 times 2 is? 8 times 2. 8 times 2 is 16. Right? That's 40, 50. 56 electrons in total. Right? Now let's count how many electrons are bonded. So each single bond, if I count single bonds, that's going to be 2 electrons. That's 2 electrons. Each double bond is going to be 4 electrons. So I'll sum all of them up and subtract it. So how many do we have? So this carbon is attached to 3 hydrogens, 3 single bonds, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There are 15 single bonds, and there's only one double bond, so times 1, and that's 30, 34. That's a total of 34, right? So 56 minus 34. What's that going to come out to be? That's 2 and 2. Oh, look at that. Pretty confident that D is our answer. I think I've done this question many times. The idea is that if you have 71 mole of benzene, let's say, it's going to give out minus 3,270 kilojoules of energy, because it's per mole. Or if you had 78 grams worth of it, because that's 1 mole, it's going to give out this amount of energy. How do I figure out for 1 gram? Can I just divide this by 78? If I divide this by 78, I'll get the per gram energy. And I'll do that for everyone. Just essentially dividing everyone by their MR. Let's see what I get. I have a feeling D is my answer. I have a feeling D is my answer. Let's take a look. I'll start with D, divide by 44. Well, that's 50. Well, that's going to be 50. And okay, 5510. Let's quickly do it. Let's not think too much. 48, that's out. It's 48. 4800 divided by, oh, that's just 48 again. And 32 divided by 78. 41, that's way off. D was the answer. 41.9. So our answer is D. Of course, that would be our answer if I had read the question incorrectly, but I actually did read it correctly. I'm just trying to cover myself up. I just noticed it's talking about least energy, right? Least energy. That's going to be A, because A has the least energy. All right, let's move on. All right, which involves reduction? So A, I think some of the more polished people in redox chemistry can understand that calcium carbonate has a charge of positive 2, the calcium does, and it'll turn into calcium oxide where the charge is positive 2 as well. And you'll realize whatever the extra carbon dioxide you're making, that also has the same charge. So the charges aren't really changing. It's not really a redox reaction. From copper to brass, it's not a chemical reaction, it's just mixing with another metal, right? So it's not even a chemical reaction, not a chemical reaction. Ethene to polyethene. Ethene to polyethene is polymerization, and yeah, if you think about it, yes, not going to. So you have to look at the bond. Let's see what's happening, because it's not getting electrons from anywhere, right? Two ethenes, if they react, this is one ethene and this is another ethene. If they react, it's not a exchange of electrons or any such thing. Another way of looking at this is because they're combining into one solid thing. So like you can't really talk about exchanges of electrons. It's not like one thing's getting poorer in electrons and the other one's getting richer. So like this bond will open up over here and this will open up and they'll join. So it's not really an exchange, right? So ethene is more or less out. I hope I explained ethene better. Like maybe in the comments, just ask about ethene. I'll talk more about the ethene, but I think it's pretty clear it's not a redox reaction. And we never highlight polymerization as a redox reaction. Sand to silicon is interesting because sand is SiO2 and it's turning to silicon. Loss of what? Loss of oxygen is classic reduction. So our answer is D, right? D is our answer. Okay, why do I do that? Why do I not forget to change every time? Huh, D, look at that. Over here, the gas has to be an acid and distinctly reacts to form a precipitate when bubbled through calcium hydroxide. Calcium hydroxide is actually lime water because it's made from limestone. Lime water. A lot of people think lime water is like nimbu ka pani, like lemon juice. It's not really. Like I know a few people who thought that, right? So the correct answer is carbon dioxide. It's talking about carbon dioxide. Answer is B. The experiment shown is used to test potassium bromide crystals. Okay, it's an electrolysis setup. The lamp does not light, partly because they're solids. Distilled water is then added to the beaker, and the lamp lights. So I guess we have to explain it. Which statement explains these results? Electrons are free to move in the solution when potassium. Electrons do not move freely in a solution. It's ions that do. Metal ions are free to move when potassium bromide melts. That's true, but that's half the story. All ions are free to move. Metal ions are free. Okay, again. Oh, when potassium bromide melts? When potassium bromide dissolves, not melts. So you're adding water. Reacts with water? Close, but it's actually dissolving in water. Oppositely charged ions, true, not just metals, are free to move in the solution when potassium bromide dissolves. Absolutely. D is our correct answer. Some drawing of bond. Now, how do I know it's H2S is like this? Sulfur is in the same group as oxygen, so it's going to behave very similar to oxygen. So I'm just copying water structure and using sulfur instead. Carbon dioxide is our answer. I'm pretty sure, unless, you know, wait, that's too many. Has only 4 electrons? Yeah, I think H2S is our answer because this has 4 electrons over here, right here. This has 8 electrons, 4 bonds. Chlorine only has 2 bonds. Chlorine over here has 2 electrons, not 2 bonds. And nitrogen has 6 electrons by looking at 3 bonds over here. So our answer is A. So over here, the electrodes aren't inert. So what's happening is, so what changes are observed during the electrolysis? A pink solid is deposited at the negative electrode. Yes. What's happening is copper from the solution is gaining electrons at the cathode, the negative charge, to form copper, right? But it's already pink to begin with. Bubbles form on the positive electrode. Well, it could have, but it would actually be at the negative electrode, right? On the positive electrode, it would end over here. The copper metal is actually losing electrons to form copper ions and electrons. So the net amount of copper in the solution isn't changing, and as it's not changing, and that's what's contributing to the color of the solution does not change. So 1 and 3 are correct. The equation shows the reaction for the formation of sulfur trioxide using a catalyst. Which change in the reaction conditions would produce more sulfur trioxide? Adding a more catalyst? Well, I won't change it because a catalyst will affect the rate of a reaction of the forward and the backward reaction. So think of a guy climbing up an escalator, right? Here's an escalator and a person is running up it, right? What a catalyst does is improves the speed of the climber going up, but also powers up the escalator, which is going down, so it goes faster. So both are going faster, but nothing is really changing, so it doesn't shift the equilibrium. Decreasing the pressure. Decreasing the pressure, or should I say increasing the pressure as I remember it, favors the side with the least moles of gas. So decreasing the pressure should favor the side with the most moles of gas. So over here you see on the left hand side we have 3 moles, 2 from here and 1 from here, and on the right hand side we have 2 moles worth of gas. So decreasing the pressure will favor the left hand side, decreasing the quantity of sulfur trioxide. Increasing the temperature, well, this is an exothermic reaction and is producing heat here. So increasing the temperature will favor the endothermic side. So again, the backward reaction is endothermic, so it'll also favor the backward reaction, reducing the amount of sulfur trioxide. So if you remove some sulfur trioxide, the equilibrium goes like, whoa, we're unbalanced. We got to have more sulfur trioxide to balance it out. So as soon as you remove some sulfur trioxide, you produce more sulfur trioxide to compensate for it. And if you recall, in the Haber's process, at least, we keep doing this. We produce a bit of ammonia, we extract the ammonia, and the ingredients go back into the chamber, and it keeps on happening until we have, well, it keeps on happening, and we keep producing more and more ammonia. All right, let's move on. The correct answer is D. Sulfur is burnt in air. So sulfur, if it burns in air, will produce sulfur dioxide. Which statement about this reaction is correct? The gas formed turns aqueous potassium dichromate from green to orange. That would be true, because sulfur dioxide does react with potassium dichromate because it can easily form sulfur trioxide, and potassium dichromate is a strong oxidizing agent. However, the colors, they're trick you. It's actually from orange to green, right? So I wouldn't blame anyone if they've selected this answer. I would have. The product is used as a food preservative. Sulfur dioxide is indeed used as a food preservative. Can't argue there. Oops. Can't argue there. And that's it. The reaction is endothermic. While you're burning it, it won't be burning if it's exothermic, right? You're burning it. That implies it's exothermic. The reaction is not reversible. Well, A, you're burning it, and it's actually this reaction which is reversible. Sulfur dioxide to sulfur trioxide. Show the correct answer is B. The compound has the following structure. Wow, look at that. Which reactions will occur with this compound? Bromine will decolorize it. I see, I spy with my little eye. A carbon-carbon double bond? Yes, it will. It absolutely will. It will react with alcohol to form an ester. Well, why not? Because I see, well, earlier I saw the carbon-carbon double bond. Now I see a carboxylic acid function group, which can readily react with any alcohol to form an ester. So this is also correct. It will react with sodium metal. Acids will react readily with metals, right? That's true. Sodium is a metal, and this is partly an acid. So this is also true. So the correct answer is C. This type of questions come a lot in A-levels. So, which of these alkanes with any one atom substituted with chlorine will not produce an isomer? So, yeah. So, if I try to replace a hydrogen with a chlorine for A, right? If I put a chlorine anywhere, say I put it here. So as long as chlorine is in the same, on the same carbon, it's actually the same molecule. So I can put it here, here, or here. It doesn't matter, right? So it's all 3 of these hydrogens will give me the same molecule. And also because this particular molecule is symmetrical. Symmetrical, how do you pronounce it? So it's symmetrical, right? If I put it here instead of here, right? Let's remove this if I can. If I put it here instead, it's the same molecule but flipped, isn't it? It's symmetrical, so it's flipped. So I'll only be able to make one sort of isomer and not many isomers. Let's take a look at B and let's see if we can make more than one. Again, let's start with chlorine over here. If I put it here, here, or here, 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 or here, it's going to be the same thing. And if I put it here, here, or here, it's going to be this molecule right here, which I've drawn, but flipped, kind of like over here, so it's because it's symmetrical still, right? But if I do not put it where it is right now, and actually put it on the central carbon, like let's say here, well, that's a new molecule, isn't it? Right? And similarly, you can have either a chlorine here or here, and it'll make two isomers. And putting it here or here would be the same thing because this molecule is symmetrical. Right? Okay, last one. You have to understand that, let me rewrite this molecule as, you know what? Think of these as three methyl groups. By methyl group, I mean CH3. Think of these as three methyl groups on one carbon, right? And one hydrogen. So it's essentially CH3 thrice. This is the molecule. So if I remove this, right, and if I put a chlorine here, I could put it here, here, or here. It does not matter because we've just used that logic. It doesn't matter as long as it's on the same carbon, it doesn't matter. But take a look at this methyl group, or this CH3. It's kind of like the same thing. So here's another way of drawing it, or another way of explaining it. Here's C with an H, and here's CH3, CH3, and CH2Cl. Is this different from the next molecule I'm going to draw, which is going to be, I'm just putting the chlorine here like that, and Cl. Because what I've done is I've taken this CH2Cl, which was here, and brought it over here, so kind of flipped it. So if this thing is either here, here, or here, it's the same thing, much like how the chlorine was the same thing here, here, or here. Think about it, right? It's a lot more clear if it's like this, right? So it's actually the same molecule. No matter where you put out of these 9 hydrogens, let me highlight them. No matter where you put the chlorine out of these 9 hydrogens, 1, 2, 3, 4, 5, 6, 7, because they're all at the end of the CH3, it's the same thing. And let me just re-highlight that relationship. Look at that, right? So if that's the case, can we make a new molecule out of it? Of course, when you put it here. And you put it here, you'll have a new molecule. Because essentially what you're doing is you have 3 CH3s like so, like so, but you're replacing, so it's going to be CCl, 3 CH3s, right? And that's a new isomer. So interesting fact, but maybe not get too caught up in how confusing this is, because they don't give it any more complicated than this. But you should be dead confident that A is your answer already. I explained it in detail because I wanted to, and I think it's good knowledge to have, especially if you're readying yourself for A levels, which is, you don't even have summer vacations before you'll start your A levels. So it's going to be right there, but A, okay, damn. A, you should be dead confident. You see A, you ignore everything else because that's how good you should be in chemistry or figuring out isomers, right? You should be confident over here about this time. Which of these processes are both endothermic? Well, cracking is endothermic because it requires energy and a catalyst to do it, right? So we know the conditions for it. Combustion is the exact opposite. It is actually quite exothermic. I mean, that's what exothermic reactions are called, especially when they react with oxygen. Combustion still is exothermic. Cracking and photosynthesis. Cracking requires energy, as we argued, and photosynthesis only happens at day. Why? Because it's taking energy from the sun. So our answer is she. Our answer is C. Fermentation. Yeah. All right, let's move on. Substance P reacts with dilute hydrochloric acid to produce a gas. So P has to be reactive enough to react with an acid, right? So I think they're talking about metal reactivity. Note that anything below hydrogen in the reactivity series, such as copper, does not react with hydrogen. So, it doesn't react with hydrogen, right? So copper's out. I think everything else is safe because lead, magnesium, and zinc are high up. So all three of these will react. Oops. All three of these will react. Okay, so what's liberated when they react? An acid reacting with a metal will liberate hydrogen gas, and this gas will react with one of these. So hydrogen, can it displace copper? Is it more reactive than copper? In copper oxide? Yes, it can. It will react because hydrogen is more reactive. Well, the same reason copper doesn't displace hydrogen earlier. Hydrogen will displace copper over here because it's more reactive, right? So our answer is D. Oops. Our answer is D. But zinc and lead are too reactive for this to take place. So this is completely not really acid metal concept checking. This is a metal metal displacement reactions which are being tested. Metal displacement reactions. The solid carbonates of three metals W, X, and Y are heated, right? So carbon dioxide given off, solid changes color from green to black. So this is very likely a transition metal. This is transitional, right? Carbonate of X. Carbon dioxide is given off solid, so this is not a transition element. I'm assuming they're talking about white carbonate to white oxide. Once carbon dioxide is liberated, carbon dioxide is not given off as solid, it does not change color. Oh, okay. Nothing happens for Y. Oops. Nothing happens for Y. The statements are correct. Metal Y is more reactive than metal X, while it's less reactive. Wait. Metal is more reactive, so it's more stable once it's reactive to the carbon. Like it's more reactive, so that in its charged form, it's more stable, or like in its ionic form. So Y is correct actually, right? Metal W is a transitional metal. We also said that. If dilute nitric acid is added to all three carbonates, carbon dioxide is given off from WX. Not, that's actually not true. Any carbonate will liberate carbon dioxide when acid is acid added to it, because this is salt analysis theory, right? You identify the carbonate ion by, in any powder, if you add acid to it and test for the carbon dioxide with lime water, you know there's a carbonate there. So 1 and 2 are correct. Let's move on. Bond breaking is endothermic process and bond making is exothermic. Thanks for letting me know. For which change is it not possible from the equation to deduce whether the reaction is endothermic or exothermic? Well, that's really easy to figure out. In A, chlorine bond is being broken and chlorine atoms are being formed and they're gaseous, right? So only bond is breaking. So bond breaking is endothermic. This reaction has an enthalpy change which is positive because it's an endothermic process, right? Over here, bonds are being broken and bonds are being formed, but we don't know their energy. So if a lot of energy was given up into breaking these bonds, but very little energy was given out when these bonds were formed, or vice versa could happen. So because both things are happening, you know, we can't tell. Think about it this way. He got robbed. Person A got robbed. So you know he got poorer, right? Person B, he didn't get robbed, but he made a lot of he business boomed and he, made a lot of profit. So obviously he has a lot more money. But person C got robbed right after the day he made a lot of profit. So is he poorer or richer? We don't know. Depends on how much did he make and how much was stolen from him. If more money was stolen from him, if he made $1,000 and someone stole 2,000 bucks from him, he got poorer, and vice versa. If he made 10,000 and someone stole 2,000 from him, yeah, like he's still rich at end of the day, or richer from the day before, right? So that's the idea. So B is out. I can't tell. It's not possible. So actually, that is the answer, right? We have to find out which doesn't. And see, you can realize only bonds are being broken, so you can tell this is an endothermic reaction. And over here, only bonds are being formed, so this is an exothermic reaction. So pretty easy, right? Exo, endo. So our correct answer is B. All right. I don't know why people are confused with this, because I guess they forget, right? So let's say if I have butene, what happens is bromine attacks, quite literally, the bond over here, right? The double bond. So if it attacks it, the bond breaks, and on each side, for each carbon, a bromine attaches itself onto it. So let me ask you this, will this ever be a possibility? Can this ever be formed? No, because when the bond breaks from here, it's going to be here or here. And if the bond broke from here, the bromine should have been on this carbon over here, right? So they have to be right next to each other. The other thing won't happen either, where the same carbon gets both bromines. It doesn't happen like that. This won't happen either. So we can clearly see they're just permutations of bromines like at different places, and you realize they're not gonna happen. This is not gonna happen because the bromine attaches with on the carbons with the double bonds, right? The only viable answer over here, the double bond was here, and this is how the bromine chose to attach itself, right? And our answer is B.